Hello, welcome back. In the next lecture, we talk about how to use ADCME to solve the Hit equation. And we compare the result with the junior solver and found that the result coincides with each other. In this lecture, we will use this program we implemented in the last lecture to do inverse modeling. That is, assuming that we have left side values, we want to estimate A and B from this data. So let's start. Let's create a new file, and let's call it ADCME inverse. Okay, in this program, we assume that the left side is null. To do that, we first execute it. Hit equal ADCME. So we have left side values. Yeah, maybe I just write it here. We just include it so that we always have the values. Okay. Yeah. Okay. So let's say our initial guess for A and B is just 1, and we want to say if we can recover 5 and 2 from this program. And to do that, let's go back to this left side. So if this is a hypothetical. Let's say our hypothetical. So let's run this program directly and say what the output is. Inverse. Okay, we have hypothetical. You can see that the hypothetical time series of the temperature on the left side is quite different from the true data. So if we run the optimizers, the optimizer will try to match this curve with this curve, and when they match, hopefully A and B will be equal to the true values. So let's see how we can do that. Because we have left side, this is a tensor, we just want to minimize the discrepancy between left side and the capital left side, which is the data. And this can be done just by creating a loss function, which is the summation of left side minus left side squared. And this loss function will be a scalar. And we want to minimize this loss function. So let's see how we can do that here. To do that, we just want to invoke our optimizer, such as ADAM optimizer or a BFGS optimizer. Let's first do ADAM. To do ADAM, you just create optimization handle here. This is how you do that. Minimize loss. Let's run the ADAM for 1000 iterations. Opt. And maybe we can just print the values of B, A, and B every 1000 iterations. Maybe 100 iterations. 1100. Maybe we can just run A and B and also loss. This is A, B, loss. We just show it. Okay, so let's run it. Yeah, you can see that this value gradually grows, and the loss function is decreasing, although kind of slowly. Yeah, after 1000 iterations, the A values grows to 1.6 and B values grows to 1.6. Yeah, and if you run the optimizers for a long time, it might converge to the true values. So let's consider another optimizer, the BFGS optimizer, which you just write something like this. And BFGS optimizer is a quasi-Newton optimizer, and it's more expensive than ADAM optimizer per iteration, but hopefully it can converge faster. So let's run this BFGS optimizer. You can see that after 12 iterations, the loss function is reduced to about 2.5 times negative 9. And what about A and B? You can see that the estimation is quite accurate, and A is 2.9 and B is 2.1. Actually, we can just drive the values to 5.0 and 2.0. The reason for the inaccuracy is that the loss function, the scaling is not very good, and you can see that it stopped because the relative reduction of f is less than some predetermined accuracy. And a very useful trick here is just multiply this loss function by 10e to the 10th power or 20th power to make the magnitude of a loss function larger, and then you run the optimizer again. Oh, you can see that you get a very good value. It's 5.0 and 2.0. Yeah, this is a very useful trick, and you will find it very useful in your homework. Yeah, that's it.